Hello friends, today we will be discussing short slab concrete pavements for high volume roads, means national highway and expressways. And the guide for this session today is IRC SP 140 2024. Now these are the concrete pavements with short joint grooves spacing of 1 to 2 meter. These are the slabs of panel size 1 meter by 1 meter up to 2 meter by 2 meter, generally in a square shape but can be rectangular also. Now as the panel size is small, load transfer will predominantly be through compression, and that gives the advantage of having the slab of lesser thickness. Design methodology which is given in IRC SP 140 is for different slab sizes, and slab size here can be 1 meter by 1 meter, 1.25 meter by 1.25 meter, or 1.5 meter by 1.5 meter, or 2 meter by 2 meter. But as I told you, it can be rectangular also, not necessarily a square slab. Then different types of foundation and different values of K, different critical loading conditions for longitudinal and or transverse bottom up and top down cracking, and with consideration of single, tandem and tridem axle loads of varying magnitude. 4 types of pavements can be designed using the procedure given in IRC code, and these 4 types cover all possible combinations of layer composition. The first type is a new construction with dry lean concrete and granular subbase or cement treated subbase placed over compacted subgrade, and a plastic or polythene or non-woven geotextile separation layer between the slab and DLC. The second type is a short slab with pavement quality concrete laid over cement treated base, which is laid over cement treated subbase and a foundation layer of 500 mm compacted subgrade, and here also we provide a polythene or non-woven geotextile separation layer between the slab and cement treated base. The third type of small concrete pavement is new construction with CTB and CTSB placed over subgrade as the foundation for short slab concrete layer with thin bituminous concrete of 30 mm to 40 mm thick as a debonding layer between the slab and the CTB. And fourth one is a short slab concrete pavement placed over new or existing bituminous pavement. So this is the existing or new bituminous layer, and below that you have GSB or CTB layer, and below that you have GSB or cement treated subbase layer, and then 500 mm thick compacted subgrade. Bituminous layer provides a non-erodible and strain absorbing support for the slab. No separation layer is required between slab and bituminous layer. A minimum soft CBR of 5% is recommended for subgrade in new construction. The data which are required to design a concrete pavement: design traffic, axle load distribution, design period, temperature differential, concrete strength in terms of pressure strength, modulus, Poisson ratio and thermal expansion, base and subbase details, and effective value of subgrade reaction. We will discuss all these parameters and then we will go for actual design problem. The first design data is design traffic, total number of commercial vehicles expected during the design period, and it is normally based on 7-day 24-hour count and a growth factor R. Traffic count should indicate daytime and nighttime traffic for carrying out fatigue analysis for top-down cracking and bottom-up cracking. Daytime traffic is generally responsible for bottom-up cracking, and nighttime traffic is responsible for top-down cracking. Cumulative number of commercial vehicles during design period is given by this equation, and this equation you have seen several times in my earlier videos. Here A is initial number of commercial vehicles per day, that is in the year when road is open to traffic. R is the annual growth rate, N is the design period, and C is the cumulative number of commercial vehicles during design period. For bottom-up cracking, the edge flexural stress caused by axial loads for bottom-up cracking is the maximum when the tire imprint of outer wheel touches the longitudinal edge. Practically, very few wheels of vehicles are tangential to the longitudinal edge or longitudinal joint of a road. Therefore, for two-lane road, take 25% of the total two-way commercial traffic, and for four-lane and other multi-lane highways, take 25% of total traffic in the direction of predominant traffic. For temperature differential, the guidelines given in IRC 58 are used. Temperature differential between the top and bottom fibers of pavements causes the slab to curl, giving rise to stresses. And in the absence of any local data, Table 1 of IRC 58, which is like this, may be used to determine the maximum temperature differential in slab of thickness 150 mm, 200 mm, 250, 300 mm to 400 mm. And these are the states, and this is the maximum temperature differential that can be used. The positive temperature differential is nearly constant for the 6-hour period during the day specific day between 10 a.m. and 4 p.m. and negative temperature differential is nearly constant for 6-hour period between midnight to 6 a.m. in the morning. Concrete strength in terms of flexural strength is required for the purpose of design of concrete slab, and this flexural strength can be estimated from characteristic strength of the concrete using this formula, which is given in IS 456. Concrete mix design is normally done on 28 days strength, but for the design of thickness of concrete pavement, 90-day strength is recommended, and 90-day flexural strength is taken as 10% more than 28 days flexural strength. E value is taken 30,000 MPa, Poisson ratio 0.15, and coefficient of thermal expansion alpha is 10 into 10 to the power minus 6 per degree centigrade. The design period for short slab concrete pavement may be 30 years, but it depends upon the designer. And several options are available for selecting base and sub-base. It can be either dryland concrete as per IRC 58, it can be cement-treated base as per 37 guidelines, or it can be a GSB layer below DLC as per IRC 58, or cement-treated sub-base as per IRC 58, or even bituminous base for new pavement as well as existing pavements. And when this bituminous base is considered, then minimum thickness of bituminous layer should be 75 mm. E value or resonant modulus of the bituminous layer at 35 degrees centigrade should not be less than 1000 MPa for existing pavement and 2500 MPa for new pavements. Another important consideration in design of pavement is K value, and this modulus of subgrade reaction value on top of DLC or bituminous pavement or cement-treated layer is considered for the design. The value of K may be selected either from IRC 58 guidelines or as per IRC SP 76 guidelines. Now this code is for design of rigid pavements and this is for white topping. And I have uploaded videos on both of these type of pavements. You can refer how to select K value as per these two IRC codes. Bond between SSCP and base. SSCP means short slab concrete pavement, and base. A debonding layer of polythene sheet of 125 micron or non-woven geotextile separation layer or a 30 to 40 millimeter thick BC layer is required. No bonding required in case of SSCP on new or in-service bituminous pavement. So when bituminous pavement is available, then in that case you do not need to provide this polythene sheet or geotextile layer. Modes of failure In short slab concrete pavement, the transfer of load applied on one slab to adjacent slab take place across all the four aggregate interlocked joints. And therefore, no double bars are required in case of short slab concrete pavements. In case of conventional large slab considered in IRC 58, one edge is longer and this larger edge is more prone to cracking. But the square slab of short concrete pavement may crack in transverse as well as longitudinal directions depending upon the position of predominant wheel path and the proportion of traffic plying close to critical load position. Available experience indicates that longitudinal cracks are most frequent, followed by transverse and corner cracks. Coming to modes of failure, flexural stress due to load and thermal stress due to temperature differential are considered. During daytime, temperature gradient is positive and slab will curve downward like this. When the axle load acts midway on the slab, maximum tensile stress is developed at the bottom of the slab and that can create a small crack here which will propagate upward, and that is why it is called bottom up cracking. This is the load position for a single wheel. This is the load position for tandem axle. One wheel here, another wheel on the next slab, and this is the wheel position for tridem axle. In case of transverse cracking during daytime, tire imprints are considered tangential to the longitudinal edge for transverse cracking. Now this is the transverse crack here because of single wheel. In case of transverse cracking with temperature gradient, the tandem and tridem axle load repetitions must be considered twice, because if you see here, this is the tandem axle and this is the tridem axle. Here first and last axle of tandem or first and last axle of tridem units are placed one after the other in the middle portion of the slab, and therefore these two categories of the wheels or axles must be considered twice. Tire imprints are considered tangential to longitudinal edge for transverse cracking and tangential to transverse joint or transverse edge for longitudinal crack. Single axle load causes the highest stress, followed by tandem and tridem axles. The position of maximum tensile strength along the length of the slab edge for transverse cracking, longitudinal cracking and corner top cracking are very close to each other and therefore can be grouped together. If the slab is designed for longitudinal and transverse cracking failure, it would also account for the check for corner cracking. Next is design traffic. For bottom-up fatigue damage analysis, 25% of total two-way commercial traffic is considered a design traffic for two-lane, two-way roads. For four-lane and multi-lane divided roadway, this 25% of total traffic in predominant direction is used for bottom-up cracking. For top-down cracking analysis, 50% of bottom-up cracking analysis should be considered. Front axles, that is steering axle with single wheels on either side, will cause very nominal bottom-up fatigue damage, and therefore these are generally neglected and only rear axle is considered. And if you recall, all these guidelines are same in IRC 58 also for design of conventional rigid pavements. The pavement shall be checked for cumulative bottom-up and top-down fatigue analysis. And for BUC, that is bottom-up cracking, flexural stress at the edge due to combined action of single, tandem and tridem axle load and positive temperature differential is considered. And for top-down cracking, damages caused by repeated cycles of axle loads and negative temperature differential, flexural stress are considered. The flexural stress is divided by the design flexural strength, that is modulus of rupture of concrete, to obtain a parameter called stress ratio. And then this stress ratio is used in this equation to determine the life consumed by the repetition of a particular type of axle. If this SR is less than 0.45, then you have unlimited fatigue life. If it is 0.45 to 0.55, then you use this equation to calculate the fatigue life. And if it is more than 0.55, then this equation is used. Cumulative fatigue damage analysis for bottom-up cracking and top-down cracking are determined using this equation, that is cumulative fatigue damage because of bottom-up cracking is summation of Ni upon Ni for a period of 6 hours 10 am to 4 pm. And CFD for top-down cracking is for the period of midnight to 6 am in the morning. Now here capital Ni is allowable number of load repetitions for the ith load group during specified 6-hour period, and Ni is predicted number of load repetitions for the ith load group during the same period. And J is the total number of load groups. So for each load group you carry out fatigue analysis, find out how much life is consumed, and then you calculate sum of all these values to get the CFD, that is cumulative fatigue damage. And a pavement is deemed to have failed if sum of cumulative damage is greater than 1. The design thickness may be increased by 10 mm to permit 2 retexturing and grinding to rectify faulting during the service life of the pavement. Let me now summarize different design steps for design of short concrete pavement slab. The first step is stipulate design value for the various parameters and size of the slab. Second, select a trial design thickness of pavement slab. Then compute repetitions of axle loads of different magnitude and different categories during the design life, and that is from axle load survey. Then find proportions of axle load repetitions operating during day and night period. Estimate axle load repetitions in the 6-hour day period. Maximum temperature differential is assumed to remain constant for bottom-up cracking. Then sixth step is estimate axle load repetitions in the 6-hour night period. Maximum temperature differential for TDC is half of BUC. A built-in negative temperature differential of 5 degrees centigrade developed during setting of the concrete is to be added to the temperature differential for the analysis of top-down cracking. That means temperature differential for top-down cracking is half of temperature differential for bottom-up cracking plus 5 degrees centigrade. Then seventh step is compute the flexural stresses at the critical locations due to single, tandem and tridem axle loads for combined effect of axle loads and positive temperature differential during the day. Determine the stress ratio and evaluate CFD for single, tandem and tridem axle loads. Then step 9 is compute the maximum flexural stress in the top surface of pavement slab due to single, tandem and tridem axle loads under negative temperature differential during night time. That is top-down cracking. Determine the stress ratio and evaluate cumulative fatigue damage for different axles for top-down cracking for selected slab thickness. Sum of CFD for BUC and TDC has to be evaluated for transverse cracking case and longitudinal cracking case separately. And then if the sum is less than 1 for transverse cracking case and longitudinal cracking case individually, then pavement is safe against fatigue cracking. If not, then you change the design thickness of the concrete slab and carry out this analysis again. Let us take one example to explain all 11 steps which I have just narrated. An example is like this. Design a cement concrete pavement of size 1 meter by 1 meter for a 4-lane divided national highway in the state of Bihar. Period 30 years. Traffic 300 commercial vehicles per day in each direction. Axle load survey of commercial vehicles indicated that percentage of front axle, that is steering axle, rear single axle, rear tandem axle and rear tridem axle are 45%, 15%, 25%, 15% respectively. Night traffic 60% and daytime traffic is 40%. Details of axle load spectrum for rear single, tandem and tridem axles are given in Excel sheet. Here front steering axles are not included. The average number of axles per commercial vehicle is 2.35 and effective CBR of compacted subgrade is 8%. Remember, this example is same as we have taken when we were discussing IRC 58, design of concrete pavement as per IRC 58. This is the axle load distribution which is obtained from the field data, field survey, single axle, tandem axle and tridem axle. Now with these data you have to design a short slab concrete pavement of 1 meter by 1 meter size. The CBR of compacted subgrade is given at 8%. Corresponding to 8%, you find out what is the value of K using this table. For 8%, it will be between these two values, and if you interpolate, it will be 50.3 megapascal per meter. Provide 150 millimeter thick granular subbase. Let us provide DLC base course of thickness 150 millimeter with a minimum 7-day compressive strength of 7 MPa as per IRC 58. So with these two values of GSB layer and DLC, which we have assumed now, effective modulus of subgrade reaction of combined foundation of subgrade plus GSP plus DLC will be taken from this table. This is also given in IRC 58. For 150 mm DLC and for subgrade of 50 point somewhere here 50.3 MPa per meter, if you interpolate these values, it will be 285 megapascal per meter. That is the final K value for your design. And let us provide a debonding layer of polythene sheet of 125 micron thickness between DLC and concrete slab. Then selection of flexural strength. Let us say M40 concrete is to be used. So that 28 days flexural strength of this concrete is 4.5 megapascal. And as I told you, the design is based on 90 days strength, and 90 days strength is taken as 10% higher. So it will be 4.95 MPa. Then design traffic. This is the equation to calculate the standard axles, that is 226 million standard axles. Now here it is for both ways, both directions, 6,000. R is 7.5% and you calculate C as 226,444,692 standard axles. And it is given in the question that average number of axles is 2.35 because of multi-axle trucks, and therefore total two-way axle load repetitions during design period is this value multiplied by 2.35, that is 532,145,025 axles. Number of axles in P dominant direction, that is 50% of this value, that is 266 million. And design traffic after adjusting for lateral placement of axles, that we take 25% of predominant direction traffic for multi-lane highway, that would be 25% of this value, that is 66,515,128. This is the design traffic. Nighttime traffic, that is 12 hours design axle repetitions, will be 60% of this traffic, because night traffic is given as 60%. So 60% of this traffic will be 39,910,877 axles. Daytime traffic will be remaining, that is 40% of this, so it will be 26,607,000. Now daytime 6-hour axle load repetition, that is half of this. Half of this will be during daytime, and therefore design number of axles load repetition for bottom up cracking will be 13,303,626 axles. Nighttime 6 hours axle load repetitions will be half of this value, that is 19,955,438. That is your for top down cracking, and therefore the summary of design traffic is that number of axles load repetitions for bottom cracking is 13,303,626, and for top down cracking it is 19,955,438. Now you have the proportion of front axle, rear axle, tandem axle and tridem axle as given in the question. So front single steering axle is 45%. So take 45% of this. This is for transverse cracking analysis. Bottom up cracking analysis, that is 45%, 15%. Now here tandem axle for bottom up cracking is to be multiplied by 2. I told you earlier. And similarly tridem axle also to multiply by 2. So these are the values, final values for analysis. For top down cracking during night time, this is not to be multiplied. Not to be multiplied by 2. Only for bottom up cracking. And similarly for longitudinal cracking, you can find out what would be the axles, category wise axle repetition. Now here when you are considering longitudinal cracking analysis, then only difference is that here you don't multiply this tandem axle, tridem axle by 2. Otherwise all these values are same. Now with these design traffic for fatigue analysis, you carry out cumulative fatigue damage analysis for bottom up cracking and for top down cracking. And these are the input parameters. And maximum daytime temperature differential in slab for the state of Bihar is 16.6 degrees centigrade. That you can find out from that table. And for nighttime temperature differential in slab will be half of this plus 5, that is 13.8 degrees centigrade. Several sets of regression equations and stress charts are developed and these are given IRC SP 140. At the same time, the entire fatigue analysis is programmed in an Excel sheet and can be used to determine whether the design is safe or not for the given input parameters and assumed slab thickness. You can make choice of slab size and with and without concrete shoulders also. So I will move to Excel sheet now to explain how this fatigue analysis is conducted using Excel sheet given along with IRC SP 140. These are the files which are provided with IRC SP 140 and you can have this slab with concrete shoulder or without concrete shoulder, and these are design of intermediate sizes and rectangular slabs. So if you open this file SSCP with concrete shoulder, then you have different size of shoulders, different size of slabs here. So we have taken 1 by 1 meter and therefore let me open this file. Now these are the input parameters which you can change. You have the input data for carriageway, 4 lane divided, slab size 1 meter by 1 meter, lane width, and all these parameters which are given in the question, they are listed here. Then these are our assumed design. Thickness of GSB 150 mm, DLC 150 mm, effective K 285, unit weight 20 days, flexural strength 4.5 and maximum daytime temperature 16.6 and trial thickness is 0.21. Let us start with 21 centimeter slab thickness, E value and Poisson ratio. And this is the Excel load spectrum data for rear single axle, rear tandem and rear tridem. You can change according to your requirement, according to your problem. Now you open this file, this will give you transverse cracking with concrete shoulders and this file is for longitudinal cracking with concrete shoulders. Now if you open it, now these input data here again imported from the earlier file and this is an Excel load spectrum and it carries out complete fatigue analysis for transverse cracking for daytime and for night time. And it finally gives you whether your design is safe or not. Sum of CFT for BUC and TDC for transverse cracking is 0.764 and therefore it says that design is safe for transverse cracking as sum of CFD is less than 1. If you consider longitudinal cracking, then again the input data is same, Excel load spectrum data is same and it gives you what is this CFT here. Now CFT here is 0. 0 for BUC and TDC. So design is safe. Now you must be wondering then when it is 0, why not to reduce the slab thickness? Let us try with 20 centimeter. Let me just change this to 0 9.2 centimeter. Now if you look at the transverse cracking, this has gone to 9.268. That is your sum of CFD for BUC and TDC. So design is now unsafe. So it will tell you here that design is unsafe because sum of CFD for BUC and TDC is more than 1. Now design thickness of the slab is 210 millimeter. Let us add 10 millimeter for 2 retexturing and grinding to rectify faulting during the service life, and therefore the final design thickness of the slab will be 220 millimeter or 22 centimeter. Thank you very much for watching this video. If you have any question, you can write in the comment box.